Next thing we're going to talk about is from a predictive standpoint. If we can take and separate the world into different categories of probability, we can start developing predictive models based on the total probability rule. And that's where decision trees really come in to help us here. In particular, right now, I'm talking about sections 5.1 and 5.2 of your textbook. And in this area, what we want to talk about is we want to look at how do we, as I mentioned, break the world into discrete groups so that these discrete groups all add up to 100%. There are lots of formulas in the book that help you through this, but I want to make sure that you get it at the concept level. Conceptually, if you look at exercise 18 in chapter 5, that is going to be in the area called exercises 5.2. What it says is that there are, in this one particular town, that we have a survey of the people in this town. There are white, black, Hispanic, and Asian people is the way that the survey broke things out. And from it, it says that there are 48% that are white, 7% Asian, 19% black, 26% Hispanic. And the next thing that it says is they took this population and divided it into two groups, either people who were obese or who were not obese. So you can see that for each one of our four branches of demographics, we can go ahead and break these down into obese or not obese. All right, from this, more information is given. It says that of the people who were surveyed, 33% of the white people were obese, okay? 49.6% of the black people who were surveyed were obese, and you see the rest of it. Once again, we're looking at 100% probabilities, which means to us that once we start going down this pipeline, if 33% of the white population is obese, then 67% are not obese, all right? So we start drawing everything to where it is a tree with main branches and with smaller branches. You will notice that all of these add up to 100%, and then each one of these other branches ends up being 100% as well, all right? So that is, we're beginning to draw the world out this way. Now, once we get to this point, we can start looking at and talking about the any questions associated with this data. So, for one question that's on 5.18, find the probability that a randomly selected person in this town is obese. Well, we know that there are white people who are obese, black people who are obese, Hispanic that are obese, and Asian that are obese. Let's go ahead and look specifically at this. We're looking at this branch. I think you see the point. The next thing we have is that from a total probability standpoint, when we are looking at the probability as we extend them out, if we take the 48% of the population who are white and then multiply that by the 33% who are obese, 0.48 times 0.33, probability says that 15.8% of the population, okay, 15.8% of the population are obese white. Same thing here, just extend it out. 19% times 49.6%, 26% times 43%. And once you go through and we gather up all of these probabilities of the people who are obese and you sum them up, that would be the total probability of the people who are obese. All right, taking it a step further. 0.158 who are white, 9.4% of the population are black obese, 11.2% are Hispanic obese, and then less than 1% or 0.6% are Asian. All of that up, and we are at 37% of the population who are obese. All right. Now we'll go back and look at another question. Given that a person is obese, what is the probability they are white? Again, these are typical questions that, you really could be looking at. If you are, in particular, if you're working at a credit union, and in this credit union, you are looking at the people who have done online banking of some sort, and you want to find demographics about those people, you would use an exact same decision tree similar to this to get you there. All right, back to this question. This is what we call a given, this is a conditional probability. And a conditional probability starts from, we give you a condition, given that a person is obese. Then the next question is, what is the probability that they're white? So we start with this idea that a given a person is obese. Well, we just talked about these people are, these are, these are, and these are. So the total is 37% are obese. Now, what about just that the next person, if we only have the obese people there, what's the probability that they are white? So if we added all those up and we got to our 37%, now we go up just the branch here that is for white and obese, that's 15.8%, okay? So given that they're obese is our total 37%, right? However, we're only looking at the white obese, that's 0.158 divided by 0.37, that's 42.7% chance that the person that is obese would be white. All right, hopefully this is beginning to make sense. What I want you to see is draw a picture to where you have the entire world set up as 100%, and then once you've done that, you can start taking the question and deciding which one of the branches you're going to go up or which of the different categories we're talking about. All right, moving one step forward, we've finished off this one and that. All right, next, we can take this and we can start applying a cost associated with it, okay? So once we draw our decision tree, we can draw in here now costs. For example, if we know that annual health care insurance is about $5,000 for people who are not obese and $15,000 for people who are obese, what's the expected annual health care insurance for any person? We have all of our probabilities from before. The way we got there was we took the percentage of people who go up this branch and the percentage of people who go up this branch, 0.48 times 0.33, and we do that all the way down. Now, let's go in and let's assign the cost for each one of these, all right? So if they are obese, it's $15,000, okay? So for this branch, we have almost 16% of the people times 15,000 is 2,370. If they're not obese, the cost is 5,000. You see how we go through and we get everything, everybody gets put in here, all right? So we have 100% of the population that's out here, 100% of the population times the cost for the demographic that's associated with them. And when we sum all of that up, we find out that the expected cost for any one person for insurance is $8,700 for this group. All right, so that's what decision trees can do. I think the most important thing about the decision trees is for you to start taking and breaking the world into questions that really can be solved by looking at the entire population, finding out what the percentages are, calculating probabilities, extending it out to an expected cost. All right, hopefully this will get you going. The question that you're working on this week is, looks like example or exercise 19, which is the very next question in the textbook. All right, good luck and let me know if you have any questions.